So welcome back. This is our third lecture about modeling with Bayesian networks. So we're going to see in this lecture more two use cases. So we're going to see more two different problems in which we can solve them with Bayesian networks. And the first one is going to be a diagnosis model from design. So it's an interesting case because given the problem description, we can figure out it's going to be the Bayesian network. And we see that the Bayesian network comes from the nature of the problem, that we want to diagnose a component in a logical circuit, in a digital circuit that is faulty, and also comes from the circuit itself that we are modeling. So I'm going to read the description of the problem, and we're going to discuss the design decisions that we have to make. So the problem is the following. So considering this digital circuit, and we have one digital circuit here as example, and it's a very simple toy example where we have just inverters and then OR gates. So consider this digital circuit, given some values for the circuit primary inputs and outputs. Our goal is to define whether this circuit is behaving normally, if not, decide the most likely health states of its components. So we have here three components, and we want to understand if those components are working or not. So we have to model this. So we will need three variables, x, y, and z, one for each component, and those variables will have two different values. One is okay, and the other one is faulty. We'll see that we can make it a little bit more specific and replace it faulty for one specific problem, for instance, stuck at 0 or stuck at 1. These are very common problems when we have digital circuits that, for instance, we have an AND gate, but the AND gate is stuck at 1, so it independent of its input, it always output a 1. It's a faulty circuit, it's a faulty gate, but stuck at 1 and stuck at 0 are very common problems that we observe in those circuits when they are not working okay. And we need evidence variables. In this case, we will provide some test case. So we're gonna provide some pairs of inputs and outputs, and in order to verify if the circuit is working okay or not. So we need one variable for each input and one variable for each output. So we have two inputs that these inputs are A and B, and we have one output that's E. So it's very simple the way that's going to work. We're going to provide the inputs. We have the circuit, so we know how to compute the output, and if the output is not the expected one, we know that something is wrong, and we will try to locate which gate is responsible or is the most likely responsible for the wrong output. So these are very clear. So these are basically the inputs and outputs of circuit and the state of the gates, but we also need some internal variables, and in this case the internal variables are going to be C and D, and these variables correspond to these internal wires here. So it's going to give us the state of the internal wires as we provide one input. All right, let's take a look at how it's going to be the Bayesian network for this example. So this is the Bayesian network for this example. So as we can see, it is the expected Bayesian network plus one additional information, that is the internal state of the gates. So we have here, for example, we have this internal wire, let's see, it's represented by a node here, C. And this node has two parents. One parent is what we expected, that is A, right? So we expected that A will dictate the state of C, because this is an inverter gate, so we expected that C is going to be the opposite of A. When A is high, C is low, and when it's low, C is high. But we have a second piece of information here, that's X. right? That will inform us if this gate here is working properly or not. So we can expect that if x is okay, remember that x can have, for instance, two values, okay and faulty. So let's suppose just these two values. So if x is okay, so the gate's working fine, and C will be the negation of A. But if x is faulty, so we don't know, right? So we can expect that maybe we have a 0.5 chance of being high and a 0.5 chance of C being low. I don't know. It's one way of modeling this problem, right? And that's going to happen for the older gates too. So if you see this internal wire D will be an AND gate. So it's going to be the end of A and B. So Y is the AND gate, and D will be the conjunction of A and B. So exactly what we expect. So we have A here as input and B as input too, but we also have this Y. And Y will tell us if this gate Y is working properly or not. So again, if Y is okay, we expect that D is simply a table that corresponds to an AND gate. If Y is not working, it's faulty, so it can be something else. Again, we can say that D can be higher or low with 0.5 probability. And finally, Z is the same thing, right? So we have at the end, it's going to be, I guess, there is a typo here. Sorry for that. We have E here on the bottom, and E is an OR gate that takes as input C and D, but also the internal state of Z. So this is interesting because this structure is general. So basically we can apply the same idea to other systems that we are trying to diagnose is working okay. It will be applicable for systems that have outputs that are determined by inputs and the health state, and do not contain feedback loops because our Bayesian networks cannot have loops. Remember, they are DAGs. And for the Ys, we have high and low values. That's fine, as expected. For the gates, we have okay or faulty is one way of modeling, or the other way it would be to have okay and the faulty a little bit more specific, so we can make like a stuck at 0 and stuck at 1, so we have like three different values. So these are the conditional probability tables for the Bayesian network. We have basically three categories of variables. We have the variables that represent the health states of the components, in this case X, Y, and Z. We have variables that represent the wires, in this case is C, D, and E. And also we have for the primary inputs A and B. So for the health variables, in this case, these health variables, we can locate them here, X and Y and Z here. We see that they have no parents. So basically what those variables will tell us is what's the probability of having those gates being faulty or being okay. So it's going to be a prior probability, and in this case here we are showing the prior probability for X, and in this case X is okay most of the time with 0.99 probability. This is one way of modeling the problem. So this we have just two states. One is okay and the other one is faulty. And this is another way of modeling the problem with three states. One is okay, the other one is stuck at 0, and the other one is stuck at 1. So in this case here, we decided to take this probability of faulty, that is 1%, and divide it by stuck at 0 and stuck at 1, and did the modeling that way. We need to create one of those tables for each variable. We are doing here just for X, and we need to decide if you're going to model this way or this way, right? So these are two different ways of modeling. We cannot do both at the same time. For the wires, so for the wires, the tables will be mostly deterministic CPTs. So we can look at here for the variable c. So it's internal y here, and we can look at the variable here, and we see that this variable has two parents. So it's going to be a conditional probability of c given x and a. So we can look at here, c given x and a. So yeah, I should invert these two tables here to be more organized, but this table here corresponds to this one. So yeah, in the case that we have just faulty. And just to take a look here how it works. So you see that we are not representing the entire table for C, because it will not fit here in the slide. We are just representing for C equal high. For C equal low is going to be equal. You just have to figure out the remaining values, but it's going to be 1 minus and the state that corresponds to C equal high. But we can look at here how it works, right? So remember that C is a inverter gate. So actually C is not inverter, X is an inverter gate, but C is going to be the negation of A. So if you look at here, and if you have A high, and the gates X is working fine, and C also high, so it should not occur, so it has 0 probability. But the other case is that we have A equal low, the gate is working fine, and C equal high. That is the expected case, so we have 1 probability. When the gate X is not working, so it's faulty, so we don't know the output. So one way of modeling that is saying that it has 0.5 probability for each possible state. So independent that A is high or low, you're going to say that C is high with 0.5 probability. In the same way, if you complete this table, you find out that C equal low is also going to happen with 0.5 probability. And this is the second way here of modeling that we have the states stuck at 0 and stuck at 1, right? And now in this case, the table is going to be completely deterministic, right? So these two cases here are similar to what we analyze in the right table, but here when we have a state that's stuck at 0, it's independent of the input. You're going to have a low output, so the probability here is going to be 0, the probability of high, right? But if we have a stuck at 1, as we have here and here, is independent of what is the input A, the output is going to be high with 1 probability. So that maps what's going to be the behavior of the gate, if it's okay or if it is faulty. And we also have, so we're going to have one table again for one of each component. So it's going to be one for C, one table for each internal Y. So we're going to have one for C, one for D, and one for E. Sorry about this. Okay, we also have A and B, and these are the inputs. So yeah, probably we are not sure about what's going to be the probability of A and B, because they will be part of a circuit and should be part of the time should be high and part of the time should be low, but it exactly probabilities, yeah, we don't know. But in this case, we put like 0.5 and 0.5 for each one, and it sounds to be like a reasonable assumption. All right, let's see what queries we can do with this model. Okay, so yeah, I guess that the most important query that we can do for this type of application is to try to understand which component is faulty. So yeah, imagine that we are working in a circuit like this that have maybe, I don't know, thousands of logical gates, and the circuit is not working properly. So you know that's not working properly because you are giving a certain input and you're measuring the output, and the output is not corresponding to the given input. And so you basically want to know which component you should blame, so you're going to go there and replace the component. So imagine that is exactly happening. So we can go to the Bayesian network and give an evidence, and this evidence we're going to be a test case. So imagine that our test case is this one, is A high. So we're going to provide high here. I'm going to say B high too, and the output is E low. And well, does it make sense or not? So let's check, right? So this is an inverter gate. So if it's working okay, this C should be low. And we have a high and high, and this is an AND gate. So this should be high. And this is OR gate, and we have low or high, and it cannot be low. So this is a problem. So I gave this evidence as input to my Bayesian network. So I set this evidence, and I want to know which component I should blame. So this is what we call the map query. It's going to give us the instantiation gap that has the highest probability. But just to make it a little bit more concrete, computing this map is like doing the following. It's not exactly like this in practice, because what I'm going to do or show you is exponential in the number of variables. So we will not do this. We're going to use a smarter algorithm for doing this. But it is like doing the following. Yeah, just to make it a little bit more concrete. Imagine that we compute the joint probability table for all possible variables. So here we're going to have all variables. We're going to have X and A and B and Y and C and Z and D and E. So here is E, right? So we have all the possible variables. When we set this evidence here, so imagine that we have one row for each possible combination of these variables values, and we also have here, I'm forgetting that we have the probability, right, associated with that. It's going to be one number associated with each possible combination of variable values. When we set this evidence, what I'm saying is that everything that does not match this sentence here should be ruled out of the table. So for instance, I have one row here that A is low. So, well, I'm just interested in rows where I have A high, B high, and E low. So I'm going to rule out this guy here. And I'm going to rule several of those rows that do not match my evidence. For the remaining rows that I have here, what I do, I look at the probabilities, and I'm going to see which one has the highest probability. This is the answer for my query, for my map query, is the instantiation that has the highest probability. So in this case, there are two instantiations that have this highest probability, and these are those instantiations. So one, for the model that uses stuck at 0 is stuck at 1, it says that Y is stuck at 0. And the second one says that Z is stuck at 0, and both have the same probability, almost 50%. So we see that all the other possible instantiations have very small probabilities, because these two dominate most of the probabilities. So it's saying basically that Y is stuck at 0. So it say, well, Y is stuck at 0, so it says that here is low, is not high. So in this case, it makes sense, because low is going to be low, okay? Or the other possible explanation is that Z is stuck at 0. So in this case here, this gate is stuck at 0, so it's always provide the output low. And if in this model here that we have just faulty or okay, the explanation is similar. It's saying that Y is faulty or Z is faulty. Right, so it's blaming the same two gates. So with this answer, we could go directly to the, in this case, to the Y and Z gates. They are the most likely the source of the problem, and replace them. So it's interesting to analyze what would happen if we have a second test case. So we're going to have a second pair of input and output, so we call it a new input vector. So we have to grow our network in order to accommodate these new variables. So if you look here, let's look at the bottom case first, because it's slightly simpler than the top one. So here we have our original Bayesian network, right? It has these inputs here that are A, B, and also the expected output, that's E here. And what we're going to do now is to provide a new here input vector that has A prime, B prime, and E prime. So it is here A prime, B prime, and A prime. Okay. So in order to compute the new states of the internal wires, we need to put this input together with the state of the gates. So for instance, for C here, what we have, so looking here at what we have originally, right? So we have C as a node that has two parents. One is X and the other is A. So here's the same thing. We have C prime that's going to take as input A prime, but also needs to know what is the internal state of X, if it's okay or faulty. The same thing is going to happen here for G prime. So G prime take as input the B prime, that is the new input vector, and also the state of Y. And also, yeah, because D is the AND gate, it has two inputs. It's going to be A prime, B prime, and also the internal state of the gate Y. And finally, E, that is the OR gate, this E prime here will be the result of the OR between C prime and D prime. There are the two internal wires, and also the internal state of the gate Z. So basically what we are doing here is growing the Bayesian network in order to accommodate the additional inputs. This top case here is also very interesting, and we are modeling when we have intermittent faults. So it is exactly the same idea. So this is the original one, and this is the extended one. So this is for the second input case. But the difference is that we are modeling the case in which we have a gate that is okay part of the time, but it's faulty for other part of the time, and it can, switch between these two states. So we have here X and X prime, right? And we have here a connection between these two guys. So I can change the state of X in the first input case. It can be okay, and in the second one it can be faulty, or vice versa. So we can model this. So this is going to represent what we call a transition probability. So we can transition X from different states, and this is going to happen also for Y here, and also for Z. So if we have this model that we can allow intermittent faults, we need an additional CPT that's going to be for X prime here, Y prime, and Z prime. But as we can see, those variables have only one parent, that is X, Y, or Z respectively. So we have a table like this, right? Is the conditional probability of X prime given X. So you're going to give us the state of X prime, assuming that the state of X is a certain value. So we can look at here the probabilities. For instance, for going from OK to OK, we have 0.99 probability. So one gate that's OK tends to stay OK. We can transition from OK to faulty with 0.1 probability. And once we are faulty, coming back to OK, you're going to be very unlikely. You're going to be 0.001 probability, and stay as faulty is going to be 0.9990. So this is what we call the transition probability of the persistency model. And it's going to apply for not only X, but also Y prime and Z prime. Well, once we have these conditional probability sets for our Bayesian network, we can come with a query. And in this case, the query is going to be very similar, going to be a map query. And we needed to set the evidence. So now, because we have more variables, that table that I mentioned to you, the joint probability table, is going to be even bigger. Now we have not just the X, A, Y, and variables, but we also have X prime, A prime, B prime, Y prime, and so on. And we need to set the variables, right? So first we set the evidence. So the evidence is going to be A equal high. It is the first test case. B equal high, E equal low. And the second one, I forgot here, but it's going to be A prime low, B prime low, and E prime low. So we can go back to the circuit and check this, but this is also an erroneous case, right? So because as E is the outcome of OR gate, and as A prime is low, but we're going to invert that and feeds the OR gate. So we are expecting here to be, with this input, we're going to expecting this to be high. So it's also a faulty case. So in this case, if we run the map, remember that we set evidence. Setting evidence is the same thing as going to the joint probability table and ruling out everything that doesn't match the two test cases. And looking for what is remaining, we're going to see that what is remaining has one instantiation with a very high probability of 97.53%, and you're going to blame the Z gate, right? So the Z should be the fault given these two test cases here. All right, so this is an interesting example and also an interesting application of what we call the dynamic Bayesian networks. And the dynamic Bayesian networks is this idea that we have an initial Bayesian network, and we start making copies of variables in order to model changes in time or space. We're going to see in future lectures some other examples of Bayesian, of dynamic Bayesian networks, include the hidden Markov models and the Markov chains. Okay, let's take a look at our final use case for Bayesian networks. And I'm going to read the description and we're going to discuss a little bit. So this figure depicts a reliability block diagram, or RBD, of a computer system, indicating conditions under which the system is guaranteed to be functioning normally available. At 1000 days since initial operation, the reliability of different components are as follows. Power supply is 99%, fan is 90%, processor is 96%, and the hard drive is 98%. What is the overall system reliability at 1000 days since operation? So these RBDs have different interpretations, and we're going to use a very simple one. So we have different blocks, and for instance, we have the power supply, we have two fans, two processors, and one hard drive. And the interpretation that we have is that a block B represents a subsystem that includes the component B and also the subsystems that are feeding into B. So for instance, fan 1 is a subsystem that includes the fan 1 and also the power supply, because the power supply is feeding into fan 1. The same thing for fan 2. And for the processor 1, because the two fans are feeding into processor 1, so processor 1 will be composed by the processor 1, the two fans, and the power supply. For a block B to be available, at least one of the subsystems feeding into B must be available. So for fan 1 to be available, the power supply must be available too, because it's feeding into fan 1. For the processor 1 is a little bit different, because we have two fans feeding into processor 1. So it will be available if fan 1 and power supply, they are both available, or if fan 2 and power supply are available. And we are interested, given that we know the reliability of each of these components, we are interested in understanding what is the reliability of the overall system. So let's take a look at how we're going to model this into a Bayesian network. So the Bayesian network is going to be more or less what we expect, right? So first, we need one variable for each component. So we're going to call the variables E, and E is going to be the power supply. We're going to have F1 and F2 for the fans, and the P1 and P2 for the processors, and D for the hard drive. And we also have a new variable that is called S, and this is for the whole system. You're going to see that S will represent the availability of the system. So we also have some intermediate variables and then ORs that are going to compose the availability of each of the subcomponents. So the Bayesian network is more or less what we expect. First, we have these root variables here that corresponds to each component, right? So we have fan 1, the power supply, the PSU, the fan 2, the CPU 1, CPU 2, sorry about this, the hard drive, and these are our root components. Each one will have a prior probability, so it's not going to be conditional. It's going to be a prior probability indicating the availability of each of those components. So some of them are 98%, other are 9%, and things like this. The logic of the problem will be implemented into the Bayesian network using AND and OR gates. So it's going to be in a very simple way, right? Based on the interpretation of the RBDs. So for instance, for the fan 1 to be available, we needed that the fan and the PSU to be available. So this is represented here, right? So we have the fan 1. So we have the fan 1, and we have the PSU, and we have this AND gate here. So this AND gate here will be indicating that both subsystems are available. The same thing is going to happen for the fan 2. The fan 2 and the PSU will be composed here by this node. For the processor, it's going to be slightly different because the processors, they have two subsystems feeding into them. So for instance, processor 1 has two subsystems. One is fan 1 and the other one is fan 2 feeding into processor 1. So what we're going to do is to first use an OR gate here to represent the availability of any of the fan subsystems. So this OR here means that or fan 1 subsystem is available or fan 2 subsystem is available, and I will compose with the availability of the processor. So here is going to be an AND gate, and the same thing is going to happen for the CPU 2. That's also composed with an AND gate here. And the AND here, what we have is similar to what we have to the processor, but just one case. So we have the hard drive that is going to depend on or the processor 1 subsystem or the processor 2 subsystem. So again, I need an OR gate here, and I'm going to take one of these two. So if both are available, it's fine, but if one is available, it's going to be enough. And I'm going to feed here into this new variable. So this is going to be a little bit different. So we're calling this variables S here is going to represent the availability of the entire system. And this variable here is an AND gate. It's going to be the AND between the availability of everything that comes from here and the hard drive. If both are available, so the entire system is available. So there are a few analyses that we can make using this model. The first one would be to compute the probability of the variable S, right? So we can ask about the probability of the variable S. So S equal avail. So I'm interested in the system being available, and I want to compute this probability here. So it's going to give us the probability of the availability of an entire system, and the answer for this query is going to be 95.9%. So we expected that 95.9% of the time the system will be available, will be working. So if you have 1,000 days, we expected that a little under 5% of the days the system was not available. Of course, that if you are system administrators, we are interested in increasing the availability of the system, right? So we can do what we call the sensibility analysis to see which components we could replace in order to increase the reliability of the entire system. And let's suppose that you want to increase from 95.9% to 96.5%. That is a small increase in the system reliability. And in this case, the sensitivity analysis is going to give us this answer. So we can improve the reliability of the hard drive to 98.6%, or the power supply to 99.6%, or the fan to 96.2%. So these are things that we can change in the system in order to increase the overall reliability. And also we can make some map queries and to see which components we can blame in case that the system is not available. So in this case, the evidence is going to be S equal to unavailable. So the system is not available. I make a map query for this, and I'm interested in the instantiation of variables that have the highest probability. So the highest probability is going to be 36%, and in this case, we should blame the hard drive, right? And this result is expected because the hard drive, if you remember, is the last component of the system, and if the hard drive fails, the entire system is going to fail. And other parts of the system, they have redundancy, right? So we have 2 fans and 2 CPUs. So yeah, it makes sense to blame the hard drive. So we could also check for the next 2 most likely instantiations. And in this case, we're going to find that both fans failed, and this has 21.8%, and the next one with 17.8% is that the power supply failed, right? So we have covered a few examples of problems and Bayesian networks, and we look at how we can create the models from the description of the problems. If you look at the book, you're going to see that the book brings a lot more use case with a lot more discussion. Unfortunately, this is a very long chapter and we cannot cover it in details. So I will let you to check the book and read the other use case in case that you are interested in understanding more about how we can model Bayesian networks from problem descriptions. We still have to make one more video that we're going to discuss a few ways to model large CPTs. So imagine that we have a CPT that has a large number of parents, how we could model that in an efficient way. So it's going to be the next video, and it will be the final one about this lecture. See you soon.